Okay, this is a video to discuss the auto-ionization of water, also known as the self-dissociation or self-ionization of water. It's based on a reaction where two water molecules bump into each other. One becomes an OH minus, the other becomes H3O plus. Okay, here I have 20 water molecules, and in a two-dimensional array. It's artificial, but it's here to try to just give a prop for the discussion. You can see that the water molecules are going to be oriented so that the hydrogens on one water molecule will be attracted to the oxygens on adjacent water molecules used by way of hydrogen bonding. Everything is still in a liquid form, so it's moving around very rapidly at room temperature. Okay. Now, the activation energy for this type of reaction, is about 1 electron volt. And the energy available through kT at room temperature is only a 40th of an electron volt. This type of reaction will not go in the forward direction very much, okay? In fact, one particular water molecule, if you focused on it, it would take 10 hours before, let's say, it would undergo this dissociation, where there is enough kinetic energy in a collision with an adjacent water molecule for an H3O to form and an OH minus to form. Once those have formed, they can now diffuse throughout the entire water volume. And the way that they would diffuse would be by the proton being transferred rather than the oxygen molecule moving around, because the oxygen molecule is much heavier. You can see here, for example, just by the change in the electrons moving around, the bonding arrangement could be changed so that this hydrogen could become associated with this water molecule nearby, and this could become an H2O bonding scheme, okay? And by this way, there is some movement in the proton, okay, but not really in the hydrogen, in the oxygen atoms, and the proton now can transfer quite fast and rapidly away. And you'll have the same type of thing that can happen on the OH minus with a proton being transferred. It would, you have essentially that the OH minus and the H3O are moving rapidly now throughout this volume. They could recombine with each other if they just happen to bump into each other, okay? Because they certainly would be energetically favorable if that were to happen, okay? The hydrogen atom by itself is going to be associated because it's very reactive. It's just a positive charge. It will be attracted to an oxygen molecule, oxygen atom. Okay, now, so the reaction that we're looking at here would be H2O plus H2O produces OH minus plus H3O plus. It has a forward direction and a reverse direction. So this is really an equilibrium. We're looking at this as an equilibrium reaction, okay? There's a certain rate at which we'll go forward, okay? That will depend on the concentration of the water molecules, okay? Which is a certain, density. It's like 1 gram per cubic centimeter at room temperature. And the temperature, which determines how much energy there is, okay? In an average collision, okay? Now, the reverse direction, on the other hand, requires a collision between an OH and an H3O minus. And that collision frequency is going to depend on the concentration of OH minus and H3O plus. So you can express that as reaction rate for the reverse is some proportionality constant times these two concentrations, okay? And in equilibrium, because we're not going to look at the complicated dynamics of what's happening dynamically, okay? Only we're going to try to first focus on the simpler, what's happening in equilibrium. And in equilibrium, you can set the generation rate of the ions to the recombination rate, okay? This is the so-called law of mass action upon which equilibrium constants are based in this form, okay? The simple form. In a reaction like this, where you have two reactants and two products, this would be expected to be very accurate. Okay, and therefore, you can show then, just simply by manipulating algebraically this constant, that the concentration product of OH minus and H3O is going to be a constant at a given temperature, okay? Now, I just gave an example where there was one ionization taking place, and certainly in this only 20 molecules, you wouldn't have this high concentration of one, but you could always have one. But for the purposes of the demonstration, I'm going to create a second one, okay? I'm going to say that there was a second ionization that took place, okay, here. And I'm only doing this to try to show how useful this law of mass action can be, the equilibrium constant. Assuming that this represented an equilibrium density of OH minus and H3O. Let me associate this in the right spot so it looks like an H3O, okay? Now, the point I'm trying to make here is, let's assume that I add some hydrochloric acid, HCl, to this water, okay? The HCl is a strong acid. It dissociates 100%, let's say. So this will immediately, upon addition, these molecules, the HCl molecules, will dissociate, and you'll end up with a concentration of, an additional concentration of H plus and Cl minus, okay? These will become, solvated or hydrated, okay, because of their own interactions. The protons, for example, will associate with the oxygens to form more H3O, and the chlorines will associate with hydrogens, to form. And they will become hydrated around. They'll become surrounded, with the protons, okay? Now, because in this case, notice I just happened to add 3 of them, so the concentration of H plus now is quite high. And the product of the concentration of H plus now has been disturbed, okay? And what that means is the reverse reaction is going to exceed the generation rate of which is constant, okay? And what's going to happen then is there will be increased collisions, so that after a time, an equilibrium has been established, the OH minus concentration has to drop, along with the H plus concentration that has to drop a little bit too because of some of these recombinations. In this particular case, I just showed one of them recombining, okay? And having done this, now if we take a look and calculate the product of the OH minus and the H3O, we see that there's the OH has dropped from a concentration, in this case of 2 to 1, and the H3O has increased from 2 to 4, okay? And you have to look at them carefully. It's because of the way I contrived it, I only added a certain amount. Equilibrium has been reestablished in this case because 4 times 1 is the same as the product of 2 and 2. And this would now represent a acidic solution of HCl. And the law of mass action now becomes very useful in calculating now, for example, the concentration of the OH minus based on this idea of equilibrium. Okay, so that's just like a little bit of an intro into acid-base chemistry and how the law of mass action, for example, would apply in an aqueous solution of H2O. Okay, thanks, bye.